This section explores in greater depth the connection between unsourced random access and compressed sensing. This view of the problem can produce many useful insights for designing algorithms, and indeed, it's been a source of inspiration for us. More specifically, in this part, we seek to accomplish three objectives. First, we want to make it clear to the viewer that every unsourced random access scheme is, in some sense, an instance of a noisy compressed sensing problem. Second, we also want to highlight some of the challenges associated with unsourced random access when viewed as a CS instance. These challenges arise from the scale of the problem, and in particular, the width of the sensing matrix. This issue can also be found in other support recovery problems in exceedingly large dimensions, such as neighbor discovery in wireless networks or distributed sketching for heavy hitters. And third, we want to introduce means to manage computational complexity for large systems. This is imperative as we are ultimately interested in pragmatic algorithms for unsourced random access. Let's first look at a basic unsourced random access setting. Here we have k active devices. Each wishes to send a B-bit message, say 128 bits for the sake of exposition. They are collectively using a multiple access channel to send their information to a wireless access point. As is customary, the signal transmitted by all the active devices will add up over the air. In this sense, the observed signal at the access point is the sum of the transmitted code words. At this point, we focus on the synchronous case, where all the symbols are synchronized. This assumption can eventually be relaxed to accommodate more realistic scenarios, but it's useful when we introduce new schemes to stay with the basic setting. So far, this aligns with the standard MAC setting. However, there are two main distinctions in the unsourced MAC. First, every active device employs the same encoder. That is, if two devices wish to send the same information bits, then they will end up transmitting the exact same signal. This forms a departure from coordinated access, where distinct users will be assigned different spreading sequences or where they'll be given an opportunity to use different codebooks. The second distinction, which really goes hand in hand with the encoding process, is the fact that the decoder must produce an unordered list of transmitted messages. In other words, the access point does not know who transmitted what. It is not responsible to assign a device identity to a received message. To understand how these characteristics turn a communication problem into an instance of a compressed sensing problem, we first look at the signal sent by a single device. Let's look, for instance, at the top device in blue. This device receives a string of bits in the form of message 1, and it maps this message into a signal that it then subsequently sends over the multiple access channel. The mapping uses encoding function f, which is shared by all the devices. Based on the encoding function, we can build a dictionary of potential transmitted signals. Starting with the all zero message, we get the first column in this dictionary through the encoding function f. Note that the time runs from top to bottom on this graph, which is a bit unusual for a signal. We do this to build a proper sensing matrix. We then move to message 1, which, when encoded, produces a second column. Repeating this operation for binary message 2, we add another column, and we can continue this process with message 3, 4, 5, and so on. Every step adds a signal to the dictionary and a column to the sensing matrix. At the end, we reach the all one message, which produces the last entry in the dictionary, or equivalently, the last column in the sensing matrix. Ultimately, we get a signal dictionary in the form of a codebook or a sensing matrix. It may be good to note that this process is generic in the sense that we've not specified a particular encoding function. We just use the fact that it exists. Given an input message, the encoder produces a signal. This signal can then be stacked as a column of the dictionary, and that's all we needed. Another notion that's important for our upcoming discussion is the index representation. We can select a specific code word from the signal dictionary by multiplying matrix phi with a basis vector. In this context, we call this vector a message index. This vector has zeros everywhere except for a value of 1 at the location corresponding to the code word we wish to select. The output signal is then equal to matrix phi times vector m. What we're really trying to do here is to think of the encoding process as matching a compressed sensing equation, somewhat. It will be instructive for future discussions if we spend a bit more time on the encoding process. At the top, we start with a binary message, say 1, 1, followed by zeros. This binary string represents a 3 in big Indian format. So the index representation has a 1 at the location that matches the 3, counting from 0. The index representation will then select the correct signal when folded over the signal dictionary. This is the signal to be transmitted. In some sense, this is obvious, but it's also important. We should keep this representation in mind as we move forward. Now that we understand the encoding process for a single device, we turn to what happens when several devices are active. Recall that in the unsourced random access paradigm, all the devices share a same codebook. So this is equivalent to all of them using the same sensing matrix phi. Of course, the column they pick will depend on the message they intend to send. Still, conceptually, they are all using the same phi. This would not be the case for a regular coordinated wireless system where users are assigned different codebooks. The wireless channel is additive in the signal space. The receive vector is the sum of the individual signals selected by the devices. Mathematically, this is the same as first adding the k-index vectors and then multiplying the resulting vectors by matrix phi. Thus, disregarding potential collisions for now, the received signal for a fully synchronized unsourced random access system is a noisy version of a matrix times a k-sparse vector. This is precisely a noisy compressed sensing problem. So let's look more closely at the type of system we have in mind. The values of the parameters we are using are heavily influenced by Yuri Polyansky's original paper, which is itself inspired by LoRaWAN, the low-power wide-area network protocol. We start with the compressed sensing interpretation, y is equal to phi times s plus noise. Vector s here is the sum of the index vectors from all the active devices. As such, s is non-negative and k-sparse. Every message contains 128 bits, and so the width of the dictionary matrix is 2 raised to the 128. The number of channel uses is roughly 32,000. Here I've picked a factor of 2 to make things easy. In this basic model, noise is Gaussian. The performance is assessed using the per-user probability of error, which was also introduced by Yuri. This is pretty close to the number of mistakes in the support recovery task, normalized by k, the number of active devices. This all seems fine. We know a great deal about compressed sensing by now. We have excellent CS solvers that are already API'd out. There's also a great theory on large compressed sensing problems with performance guarantees. So what's the catch? From a pragmatic point of view, a width of 2 raised to the 128 is huge. Even using sensing matrices amenable to fast techniques, such as a fast Walsh-Hadamard transform, we can only get to width on the order of 2 raised to the 20 or so. Existing CS solvers are doomed. They will simply not execute at the scale we're interested in. Let's look at where that puts us on the sparsity undersampling trade-off curve. Again, these two functions are from a 2009 paper by Donohoe, Maleki, and Montanari. And they should be taken somewhat lightly here because they do not match our problem exactly. The red curve is perhaps closer in spirit to what we're trying to do. The undersampling fraction is the number of channel uses divided by the width of the matrix. So we have 2 to the 15 over 2 raised to the 128. It's essentially 0. The measure of sparsity is k, which is a couple hundred devices at most, divided by the number of channel uses. With 256 active devices, we have a measure of sparsity of 2 raised to the minus 7. So really, an unsourced random access system is operating very, very close to the origin. The question then is, how can we use the fact that the system is operating in the bottom left corner into addressing the width of the sensing matrix? Let's survey quickly some candidate solutions to this problem. The first idea is simple. It's to divide the problem into subcomponents by using a block diagonal sensing matrix instead of a full matrix. In this case, the effective width of the block components is reduced. If the original matrix has 2 raised to the 128 columns, then a block diagonal matrix with L blocks will essentially give L independent CS problems, each with a width of 2 raised to the 128 divided by L. Of course, this alone will not solve our problem because assuming that we can handle matrices up to a maximum width of 2 raised to the 20, this means that we'll have to solve 2 raised to the 108 parallel CS problems. Nevertheless, it's good to keep this strategy in mind as a possible tools which we can combine with other strategies. The second approach is to use the power of error-correcting codes. Conceptually, we can view a codebook as a sensing matrix. Then, coding theory has been very successful at designing wide sensing matrices where a sent message can be recovered from its observation. Here, 128 bits leads to a small block code. In some sense, a small coding problem is a very large compressed sensing problem. To implement this scheme, we can have several codebooks available to the devices. In this example, we have 2. A device can then select a codebook based on the value of a few message bits. It then encodes the remainder of its message using the chosen encoding function. At the receiver, the access point can seek to recover the transmitted code words by decoding the various codes. There are 2 challenges with this approach. On the one hand, coding theorists have been very successful at designing powerful codes for a single user. Yet, much less is known when multiple users are concurrently adopting the same code. Second, the number of devices selecting a particular code is unknown. It must be estimated at the access point. To make this strategy work, one has to mitigate potential collisions among devices choosing the same code, and one also has to provide an estimation strategy for the number of devices who have chosen a particular code. The last approach we wish to mention in this video is based on data fragmentation. The idea is to partition the binary message a device wishes to send into fragments before using indexing. For instance, if the original message contains 128 bits, then we can create 8 fragments of 16 bits, a manageable size. This leads to 8 CS problems, each with a sensing matrix of width 2 raised to the 16. In this case, standard CS solver can be employed, and the individual fragments sent by the devices can be recovered. The 8 output lists are, of course, unordered, so this leaves a bit of an issue. The access point has to perform disambiguation. It has to decide which fragments go together to produce a message. We will come back to this issue shortly. Let's see what happens with data fragmentation on the sparsity undersampling trade-off curve. As we partition the problem into smaller subcomponents, both the undersampling fraction and the measure of sparsity increase. The undersampling fraction delta, for instance, is going to be equal to 2 to the 15 divided by L times 2 raised to 128 divided by L. And so delta increased very rapidly with L. Likewise, the measure of sparsity, rho, is equal to L times 256, say, divided by 2 to the 15. So here rho becomes linear in L, with the measure of sparsity being L divided by 2 to the 7. So you can see these points on the bottom. These points are obtained by progressively larger values of L, going from 1 in the corner to 8, 9, 10, and 11. So we can see that data fragmentation significantly changes our operating point on this graph. We summarize the finding of this section on this slide. At the top, we have the standard noisy compressed sensing equation. Observation y is equal to sensing matrix phi times sparse vector s plus some noise. We know that unsourced random access is an instance of a noisy support recovery problem. For this problem, we have full control over the matrix phi. The width of the matrix, however, is huge, so we need some good strategies. In developing these strategies, there's an aspect of randomness that's associated with the uncoordinated nature of the problem. We've also surveyed some strategies that we'll apply later to get some pragmatic solution to unsourced random access. In particular, we've looked at sparsifying collisions. We've seen how we can try to leverage advanced coding and spreading to come up with good scheme. And we have this notion of data fragmentation, which is a divide and conquer approach based on partitioning the initial message. On this last slide, we give some pertinent references for the material we've presented in this section.